Hello everyone. In this lecture of the probability theory course, we will be giving an introduction to probability. We will start with random experiments and probability, and then we will explain what is meant by sample space and events. Then we will learn how to use Venn diagrams to find number of elements in events. And finally, we will mention the axioms of probability. Let's first start with the definition of random experiments and some applications for probability. A random experiment is defined as an experiment whose outcome cannot be predicted for certain. So we might know all the possible outcomes of a certain experiment, however, we are not sure which of these specific outcomes will result in a certain run. For example, if you are rolling a die, we know that the outcome will be one of the 6 faces of the die. However, we are not sure during a specific roll which will be the specific face resulting in. Similarly, for a football game, we are not sure which of the possible outcomes of that game, winning or losing or drawing, will be the result for your favorite team. In buying a stock market, we are not certain whether the stock price will increase or decrease, and for the random experiment of beating Thanos in the Infinity War, there is no certainty whether the Avengers will win or lose. Probability is usually associated with random experiments because each of the possible outcomes of the random experiment has certain probability. That's why the probability theory has many applications in real-life problems, such as hypothesis testing, where we have two hypotheses, null hypothesis and alternative hypothesis, and we are usually interested in certain types of errors. This can be also an application for probability of error calculations in digital communication systems. Also in machine learning, we have what is called the ANOVA testing, in which the statistical significance of the difference between two groups or two sets of data is sought, and also in some applications such that modeling certain elements in aerospace industry, we are interested in calculating the survival probability of the metal components of any of the industry parts. Let's now focus on sample space and events. A sample space is defined as the set of all possible outcomes of the random experiment. So, as we mentioned earlier, a random experiment has many outcomes from which we are not sure which one of them will arise. However, we know all the possible outcomes. The set of all these possible outcomes is what we call the sample space. And each of the outcomes of such experiment is called an element, a member, or a sample point. For example, if we have an experiment consisting of flipping a coin, and if the experiment is just flipping a coin, so we know that the outcomes of the experiment are either head or tail. In this case, the sample space, usually denoted by capital S, is written as the set of head and tail. Each of these two elements, head or tail, is called an element, member, or a sample point. However, in this example, the experiment is not just flipping a coin. As we continue reading, the experiment is or consists of flipping a coin, then flipping it again if a head is the outcome, and if tail is the outcome, a die is tossed. So actually the experiment doesn't stop at flipping a coin. Once we flip a coin, we know that the possible outcomes are head or tail. And if the outcome is head, the coin is flipped again, for which case the second part of the outcome is also either head or tail. However, if the outcome of the first flip of the coin is tail, we roll a die whose outcome can be one 2, 3, and up to 6. So the outcome in each of the random runs of this experiment is composed of two parts. The first part is always a face of a coin, which can be either head or tail, and the second part depends on the first part of the experiment. So if the first outcome of the experiment is head, then the second part is again a face of the coin. However, if the outcome of the first part of the experiment is tail, then the second outcome will be a number from 1 to 6. So if you want to write the sample space in this case, we might choose to write it in this form. Each element is composed of two parts. The first part resembles the outcome of the first part of the experiment, and similarly the second part. In this case, we have head, or head, tail, because these are the two outcomes related to the first outcome of the experiment being head, and then the remaining elements are tail and 1, tail and 2, and so on till tail and 6, which represent the outcome of the experiment in the second case, where the first coin flip is tail and then we roll a die. Another example, if we have the sample space expressed as the set of ordered points or Cartesian points x and y, where x squared plus y squared is less than or equal to 5. This equation represents the equation of a circle surface whose radius is square root of 5. And of course, since this is an inequality, not equality, so the points achieving this inequality are all the points inside this circle. So if the experiment is choosing a point which satisfies this equation, so the set of all the possible outcomes, or the sample space, is the surface of a circle. Here we can notice that the number of elements of a sample space can be either finite, such as in the first example, or can be infinite, such as in the second example of the surface circle. Let's now define what is meant by an event. An event is defined as a subset of the sample space. So an event is usually used to describe a subset of the possible outcomes of a random experiment. So for example, if we roll a die, the outcomes are known to be any number from 1 to 6. If we want to specify an event in which the outcome of this experiment is odd, then this is a subset of the sample space, and the named event contains only the odd numbers from 1 to 6, which are 1, 3, and 5. Another example as shown here, it says that the sample space represents the lifetime, denoted as t, of an electronic component in years. In this case, the sample space is represented by integer numbers representing the lifetime of the electronic component in years. And if we agree to consider any part of a year is a complete year, in this case the lifetime can be either 1 year, this is anywhere from 1 day to a whole year, or 2 years, which is 1 complete year or any part of the second year, and so on. So the sample space in this case is the set of all natural numbers, or the set of all counting numbers. If we determine or we define an event A in which the component fails before the end of the 5th year, in this case, what will be the possible lifetime of all the components included in event A? So this defines that a component fails by the end or before the end of the 5th year, which means that it can fail within the 1st year, 2nd year, 3rd, 4th, or 5th. So as we can see, event A is a subset of the sample space S. This example is also good for us to discuss when can we consider a set countable and when can we consider it uncountable. Usually finite sets are countable because we can count the number of elements. However, the reverse is not necessarily true, which means that infinite sets or sets which includes infinite number of elements are not necessarily considered uncountable. Actually, if there is a pattern or a sequence that describes the elements of this set, even if these elements are infinite, this set is still considered countable. For example, let's consider the set of the multiples of 3, the positive multiples of 3. So this set can be written as 3, 6, 9, 12, and so on. Obviously, this set is infinite or includes an infinite number of elements. However, in the notion of being countable or uncountable, this set is considered countable because simply we can name the ith element of this set. For example, if we want to determine the 3rd element of this set, so this will be for sure 9. The 3rd element in this case is the 3rd multiple of 3, which is 9. The 4th element is 12. The 10th element is 30. So we can name any element of the sample space or the set, and that's why we consider it a countable set. On the other hand, if the set is infinite and there is no pattern or there is no sequence that governs or can be used to describe the elements of this set, in this case the set is uncountable. So for this example, the lifetime of an electronic component in years, which is the set of counting numbers or natural numbers 1, 2, 3 up to infinity, is a countable set. This notion will be useful when we come later on in defining what is called discrete random variable and continuous random variable. Let's now move to another definition, which is the definition of the complement of an event. The complement of an event with respect to the sample space is defined as all the elements in the sample space that are not included in the event. So in this example, the complement of event A is all the numbers in sample space S that are not included in A, which are the numbers from 6 to or the integers from 6 to infinity. That's why it is important when we talk about the complement of an event to determine that it is considered with respect to a sample space, because it's all the elements in the sample space that are not included in the event itself. Let's now define two important definitions. The first of them is the intersection of two events, A and B, usually denoted as we can see here, E and A intersection B, and the intersection of the two events A and B is the event containing all the elements that are common to A and B. Please be careful here that the use of the word and doesn't mean that we are considering all the elements in A and B together. We are only considering the elements that are common to A and B. So the intersection of two events is the event that includes all the elements that exist in both A and B, not any of the elements in A and B, only the common elements in A and B. Let's understand this through an example. If the experiment we are considering is tossing a die, which means that the sample space will be 1, 2, 3, 4, 5, and 6, the faces of the die. Let's now define event A, which is the event of having a number which is greater than 3. Of course, having a number in rolling the die. So event A will be the set of elements. Number is greater than 3, which means starting from 4, 5, and 6. And the event B is defined as the event in which that number is less than or equal to 5. So that's 1, 2, 3, 4, and 5. Now, if we consider the intersection of the two events A and B, so that will be the elements common in A and B, which obviously are 4 and 5, because 4 and 5 exist in both A and B. So this is the set of the intersection. In case that intersection includes no elements, we consider that the two events are mutually exclusive. So the definition of mutual exclusive events, or sometimes we call them disjoint events, is when the intersection of the two events is equal to phi, or null, or the empty set. So that means that no elements are common in A and B, or no element exists is a member of the set A and B altogether. So for example, if we consider an event A, which is the number is less than 5, and B, which is the number is greater than or equal, A is the event in which the number is less than 3, and the event B is the event in which the number is greater than or equal to 5. Obviously, there is no element that can be less than 3 and greater than or equal to 5 at the same time. So here the intersection between A and B is equal to phi, and we can consider these two events A and B are mutually exclusive or disjoint. The second important definition about the relations between events is the union. The union of two events A and B, usually denoted as we can see here, A union B, is the event containing all the elements that belong to A or B or both. So again, here the wording is very important in understanding the definition of union. The union of two events is all the elements that are in A or in B, or which are common between them. So any elements that is in A only, or in B only, or in both of A and B, that will be an element in the union of A and B. So again, back to our experiment in which event A is the event of numbers 4, 5, and 6, and the event B is the event of numbers 1, 2, 3, 4, and 5. The union of these two events is all the elements from 1 to 6. In the other example, in which event A is 1, 2, which are the numbers less than 3, and the event B, which are the numbers greater than or equal to 5, this is 5 and 6. In this case, A union B equals all the elements in A and B, which are 1, 2, 5, and 6. Let's now talk about Venn diagrams, which can be used as an effective method to explain the relationships between various events which are members of a sample space. Let's value the importance or the usefulness of Venn diagrams through an example. Let's consider an example in which we have a class of 260 senior students. 93 of those study Spanish, 95 study chemistry, and 165 study mathematics. Of course, someone can wonder right now, where did we get all these numbers which are now exceeding 260? So if we have 63 studying Spanish, 93 studying Spanish, 95 studying chemistry, 165 studying mathematics, the total of these three numbers is definitely larger than 260. However, this consideration or this assumption is not correct, because when we are told that 93 study Spanish, that does not mean that they study Spanish only. Similarly, for those 95 studying chemistry and those 165 studying mathematics, no one mentioned that they are studying only one subject. So out of those 196 studying mathematics, some of them which are studying Spanish are already included in these 93. So we can expect that in general, some students or the students which study Spanish and mathematics are counted both in these 93 and in this 196. So the 93 students studying Spanish are not necessarily completely different from those 95 students studying chemistry. Let's proceed with the example and we will understand it in more clear way. Now we are being given the number of students, 18 students studying Spanish and chemistry, 75 who study chemistry and math, 20 who study math and Spanish. Again, out of those 20 which study math and Spanish, some of them might be also studying mathematics, studying chemistry, and some of them might not be studying chemistry. Now with the last part of the example, we have 15 students who are studying the three subjects, which means that we have, out of the overall 260 students, we have 15 students that are studying all three subjects, Spanish, chemistry, and math. So now if we are wondering how many students are not studying any of the three subjects, how many students of the 260 are not taking Spanish, nor chemistry, nor mathematics, how would we find this number? Venn diagrams can be used as a useful tool to help us answering this question. So let's assume that we have that box representing the overall number of students, the 260 students, or in this case our sample space. So we can consider that we are having an experiment in which we choose a student from those 260 seniors, and this student can be either studying Spanish only, chemistry only, mathematics only, or any pair of the three subjects, or the three subjects at the same time. So let's consider, or let's assume that this box represents the sample space. Then we can have event, for example, Spanish, drawn as a subset of the sample space. As we defined, any event is considered as a subset of the sample space. So this set includes the students who study Spanish. Definitely we know that this subset includes 93 students overall. Now, if we want to draw the subset which represents chemistry, let's first assume that we will draw it this way. So this is the set of students who study chemistry, and we know that the total in this set is 95 students. However, we already know that some students study both Spanish and chemistry. Actually, those are 18 students who study Spanish and chemistry. So there is an intersection between these two events. In order to show such intersection, we have to draw C such that it has an intersection with set S, which represents Spanish. In this case, we cannot write 93 here because we are not sure till this moment how many of the 93 is studying Spanish only and how many of them should be in this intersection, which is the intersection representing students studying both Spanish and chemistry. Similarly, for the set of students studying math, if we want to draw it in a correct way or in a general way, we have to draw it such that it has intersection with chemistry, it has intersection with Spanish, and it has intersection with both Spanish and chemistry. So as we can see here, this area represents the intersection of the three sets, Spanish, chemistry, and math. This area represents the intersection between math and chemistry, and I intentionally included this part which represents the intersection of the three subjects, and so on. Now let's fill each of these spaces with the number of students that we know about. And in order to do it without any mistakes, we have to start with the most determined set. The most determined set is the set of students studying all three subjects. So these are 15 students. These 15 students are necessarily the students in this intersection, which represents students studying those three subjects. Now let's consider the 20 students who study math and Spanish. So the intersection between math and Spanish is this space or this area, of which 15 were studying the three subjects. So how many of the 20 is left such that those are studying math and Spanish but not the third subject, which is chemistry? Of course, these are 5 students which are studying Spanish and math only. If we count the total number of students in this intersection, will be 20 as in here. Let's do one more. Considering the students studying chemistry and math, so this is the intersection between chemistry and math. In total, they are 75. However, we know that 15 of them are studying the third subject as well. So the 60 remaining students are studying chemistry and math only. Continuing in this manner, we can find the number of students in each of these subsets, and the remaining students that are not included here are those students which are not studying any of the three subjects. And here we can see the Venn diagram after being entirely completed. As you can check the number of students studying, for example, Spanish, is the total of those studying Spanish, chemistry, and math, those 15, in addition to 5 studying Spanish and math together, and 3 studying Spanish and chemistry together, and 70 studying only Spanish. The total of these numbers is equal to the 93 students who are studying Spanish. If we go back to the main question, which is what is the number of students who are not studying any of the three subjects, so we can count all the students studying any of the three subjects alone or together with another subject or with the other two subjects, which will be a total of 255, and we are left with 5 students who didn't study any of the three subjects. If we want to calculate the probability of finding a student who didn't study or who doesn't study any of the three subjects, that will be 5 out of 260 students, because this is the chance of finding such a student. It's 5 chances out of 260. if we want to find the probability of finding a student who studies chemistry only, so that will be 17 out of 260. And more about probability and the axioms of probability will come later in this lecture. Using Venn diagrams can be also useful in finding many of the useful relations between sets, such as, for example, the intersection between any event A and phi. Again, the intersection was the set of elements which exists in both two events together or both two sets together. However, since the phi or the null set includes no elements, so definitely the intersection here will be phi or the null set. On the other hand, the union of a certain event and phi, which is all the elements in A or phi or both of them, so that will be set A. The intersection between a set and its complement is phi, because the complement of an event is all the elements in the sample space and not in event A. So definitely there is no intersection between an event and its complement, or the event and its complement are mutually exclusive or disjoint. But their union is the set of all possible elements, those in A and not in A but in S. So their their union is the entire sample space. Also, it can be simply concluded that the complement of the sample space is phi, because there is no element in the sample space but does not exist in the sample space, which is the definition of the complement of an event with respect to the sample space. So the complement event of the sample space is phi. The complement of a complement of an event is the event itself, because it is the elements in the complement, but sorry, it's the elements in the sample space but are not in the complement, which are the elements in the event itself. The last two relations are known by the De Morgan laws, and they say that the intersection of two events when complemented will be the union of the complementary events, and on the other hand, the complement of the union of two events is the intersection of the complement of each of the two events. Each of these two relations can be simply proved using the Venn diagram. For example, if this is the sample space and this is event A, and in general this is event B. So let's consider the complementary of the two events. So the complementary of A is this green shaded space, or the elements outside A, and the complementary of event B is this blue shaded area, which is all the area outside B. Now, if we consider the complement of the intersection of two events, so this is all the shaded area except, or all the space except the unshaded area, because the unshaded area or the yellow shaded area here is the intersection. So the complement is the remaining part, which are the parts which are shaded green only, like here, or shaded blue only, like here, or shaded green and blue. This is the definition of union of two events, where the two events are the green and the blue, which are the complement of A and complement of B. So the complement of an intersection of two events is the union of their complements. Similarly, if you consider the intersection, let's do it starting from this side, the other relation, the intersection between the two complementary events, which is the intersection between the green shaded area and the blue shaded area, is the area outside these boundaries. If you look closely, only outside this boundary we have area which is shaded with both green and blue, which is the intersection of these two, and this is all what is outside the union of A and B, or simply the complementary of A union B. So instead of memorizing those relations, Venn diagrams can be simply used to prove these relations whenever needed. Now for the final topic of this lecture, let's discuss the axioms of probability. The axioms of probability are three axioms which arise from the concept of probability, and they do not need to be proven or driven because they are logical axioms, and these axioms are as follows. The first axiom is that the probability of any event is larger than or equal 0 and less than or equal 1. Of course, the probability of any event is a non-negative value because it has no meaning. It is the chance that one of the outcomes included in this event become the outcome of the experiments. This is definitely a positive number. So it can be 0 if event A has no elements or cannot happen. So for example, what is the probability of having number 8 when we roll a die whose faces are numbered from 1 to 6? This event is impossible or has a probability of 0. However, there is no event that can have negative probability. And the other side of this inequality, we cannot have a probability which is larger than 1, because any event whose probability is equal to 1 is an event which coincides with the sample space, or which includes the sample space entirely. So for example, if we ask what is the probability of having a face on the die either 1 or 2 or 3 or 5 or 6, actually these are all the possible outcomes. So definitely we will have one of these 6 numbers. So if we are calculating the probability of event including all the outcomes, the probability is equal to 1, or we have certainty, 100% certainty of this event. For general events, the probability of having such event ranges between 0 and 1 with possibility of equality. And the second axiom, which we already used to justify the equality on the first axiom, is that the probability of the sample space is equal to 1. So the sample space is certain. If you recall what we defined the random experiment, it's a random experiment whose outcomes are known, but a certain outcome is not certain. We know that the outcome will be one of the elements of the sample space, but we do not know which of the outcomes or the elements will be the one during a specific run of the experiment. And the third axiom is related to mutually exclusive events or disjoint events. So if we have events A and B which are disjoint, then the probability of their union is the probability of event A alone plus the probability of event B alone. This addition rule also is a logical rule and makes sense, because if two events are mutually exclusive, then the union is just the elements in A and the elements in B. So the probability of having the union of two events is either having one of the elements in A, which is the probability of event A, or having one of the elements in B, which is the probability of B. So for example, if we have event A equals to a number on the die which is being rolled, and this number is less than or equal 3. So this is the event of 1 and 2. And B is the event of having a number larger than or equal 5. So that is 5 and 6. The union is definitely 1, 2, 5, and 6. What is the probability of event A? Probability of event A is equal to 2 over 6 because event A includes 2 elements, while the sample space includes overall 6 elements, and all the elements are equiprobable, which means that the probability of A is equal to 2 over 6. Similarly, the probability of B is equal to 2 over 6. If you consider the union, it will include 4 elements whose probability is 4 over 6, which is 2 over 6 probability of A plus 2 over 6 probability of B. So these 3 axioms represent the axioms of probability, or the basic fundamental rules which govern the probability, and they come without proof. Also, it's important here, or it's useful to mention that if the elements of any event or the elements of any of the elements of a sample space are not equiprobable, then we use this rule to calculate the probability of the event. So let's imagine that our die is not balanced in the sense that probability of having face 1 is equal to half, while the probability of having face 2 or face 3 or face 4 or 5 or 6 are equiprobable. So these 5 probabilities are equal to each other. First of all, what will be this probability equal? What will be the probability of having 2, 3, 4, 5, and 6? Since the probability of having face 1 is equal to half, and the probability of the sample space itself is equal to 1, so that means that the remaining probability after considering having face 1 is equal to the other half. So the probability of 2 plus the probability of 3 plus 4 plus 5 plus 6 should be equal to half. And since they are equiprobable, so each one of them is equal to 1/5 of that half, which is 1 over 10. As a double check, if we add the probability of each of the possible outcomes, they come to the total of 1. Why did we add the probabilities of each of these outcomes? Because each of these 6 outcomes is mutually exclusive, or each of these events, where each event includes only one outcome, are mutually exclusive. So the third axiom come handy in this case. So the probability of 1 plus the probability of 2 plus probability of 3 plus the probability of 6 equals the probability of the reunion. However, the reunion is the sample space, which has a probability equal to 1. Now, if we consider the probability of event A under this consideration, so the probability of event A can be considered as the union of 2 events. Event of them includes 1, and event of the other includes the outcome 2. And since these 2, let's say, sub-events are mutually exclusive, then the probability of their union is the addition of their probabilities. The probability of 1 equals to half, and the probability of 2 is equals to 1 over 10. So the probability of A in the case of this unbalanced die equal to half plus 1 over 10. On the other hand, the probability of B is equal to probability of 5 plus probability of 6, which is 1 over 10 plus 1 over 10. of course, the probability of the union of A and B will be equal to the addition of these probabilities. So it's very important to note that in general, the outcomes or the elements of the sample space are not necessarily equiprobable. However, the summation of their probabilities is equal to 1 using these two axioms, because the elements themselves are mutually exclusive. So the probability of their union equals the addition of these their probabilities, and their union constitutes the sample space itself, which has a probability equal to 1. From these axioms, some basic rules arise. The first of them is the probability of a complementary event is equal to 1 minus the probability of an event. And again, this can be concluded or proven using the axioms of probability, because we know that A union its complementary is equal to the sample space. So the probability of A union its complementary is equal to the probability of the sample space. However, since A and A dash are mutually exclusive, so axiom 3 said that this will be the probability of A plus the probability of A dash. And from the second axiom, the probability of the sample space is equal to 1. So the probability of A will be equal to 1 minus probability of O complement, or the other way around, probability of A complement will be equal to 1 minus probability of A. Another basic rule that is used a lot is the probability of union of two events in case the two events are not mutually exclusive. If they are mutually exclusive, from axiom 3, they will have probability of A plus probability of B, but since in the general case they are intersecting, or there is an intersection between them, then we have to exclude the elements in the intersection because they were counted twice in these two probabilities, in which case the probability of union of two events is probability of event A plus probability of event B minus probability of their intersection. This rule is general enough that we can use it even for mutually exclusive events, because in this case, if they are mutually exclusive, the intersection is equal to phi and the probability of the null event is equal to 0, and this rule reduces back to axiom 3. So in summary, this lecture covered the definition of random experiments and the notion of probability and its use in real-life problems. We defined what is meant by sample space, what is meant by events, as well as the relationships between events, such as the complement, the intersection, and the union of events. We showed how to use Venn diagrams to find the number of elements in different events and the relationships between the different events. And finally, we discussed the axioms of probability.